Welcome back, mathematicians. We're now going to take a look at these examples of projectile motion, bearing in mind the physical description that we had earlier on. So, we've got a ball which is thrown with an initial velocity of 40 meters per second and an angle of inclination of 30 degrees to the top of a stand 25 meters above the ground. So the first thing we need to do is draw a sketch, so we can get a reasonable idea of what's going on physically, and then write down all our information for the vertical and horizontal components. So our sketch will look like this. So there's our stand 25 meters high. We'll take this point as the reference point, so we'll let that be where x equals 0 and y equals 0. The angle of inclination is 30 degrees, and the projectile launch velocity is 40 meters per second at 30 degrees. And we can write down that horizontally the acceleration is 0, vertically it's minus 10. Now we then integrate. So if we look at the horizontal side, the initial horizontal velocity is just our 40 cos 30, so it's our component of the vector here in this direction. So we know that's 40 cos 30. If we can evaluate, because it's an exact angle, it's often helpful to do that. So that's 40 times root 3 on 2, which is 20 root 3. We can then integrate again to get displacement, so that will be 20 root 3 t plus our constant. And because we said when t equals 0, we'll let x equals 0, that gives us that c equals 0. So this is our equation for horizontal displacement. So we've got two equations, horizontal velocity, horizontal displacement, and of course our initial equation, 0 acceleration horizontally. On the other side, vertically, from our acceleration equation, we integrate and we'll get minus 10t plus c. When t equals 0, v is 40 sine 30, which of course is 40 times a half. That gives us that c is 20, so our velocity equation is 20 minus 10t. If we then integrate that again, then find our constant of integration, because when t equals 0, we said we would let y equal 0. We could have also said we'll let y equal 25, and in that case our reference level would have been the floor or the ground. But we've chosen to go with the top of the stand as the reference point. So our displacement equation, vertically, relative to the top of the stand, is 20t minus 5t squared. Now what we then need to do is to find the 6 coefficients of motion. We've done that. Part B, find how far the ball rises. So, how far the ball rises is the time that it takes. It depends on the time it takes to get the vertical velocity 0. So that will happen when this occurs, which will be at 2 seconds. So when t equals 2, what is the vertical displacement? So we put it into our equation for y, and we get 20 meters above the stand, or 45 meters above the ground. The actual velocity then, when t equals 2, the vertical component of velocity is 0, the horizontal component of velocity is always 20 root 3. So at the top of the parabolic arc, the velocity is only 20 root 3 horizontally, and it actually said what's its speed when it is there. So its speed is just 20 root 3. I've said in the horizontal direction because I'm describing the vector, but the 20 root 3 is just the speed. We don't have to specify the direction. We'll see later on that if it wasn't at the top, we would have to combine vectors, but we'll get to that later on. The horizontal position, so this is now how far it is horizontally from the stand. We just want the value of x, given that the displacement horizontally is 20 root 3 t, and we know that t is 2 seconds, so that will be 40 root 3 meters. Now to get the time of flight, the horizontal range and the impact speed and angle, so a few little bits and pieces here. For the time of flight, what we want is the time that it takes until the particle gets to minus 25 meters. so until it goes up and comes down here. So that is just reflective of where we took the origin to be. So we're going to solve our displacement equation in the vertical direction. So if we simplify that by dividing through by 5 and shuffle it into the form of a quadratic, we can see that we get two factors. Only one of these, which is the 5, makes any sense physically. So we ignore the -1. It's sort of like a projection back into time, if you like. So it takes 5 seconds for the ball to hit the ground, so that's the time of flight. The horizontal range is simply how far it went, so we want x when the vertical displacement was -25, which happened when t equals 5 seconds. So x is 20 root 3 times 5, the horizontal velocity times the time for which we were travelling with that, so that's 100 root 3 metres. So it hits the ground 100 root 3 metres from the bottom of our stand. Now to get the impact speed and angle, then we have to realise that we've got two vectors operating. We've got this unchanging horizontal velocity acting like that, and we've got a changing vertical velocity, so we've got to find the value of that vertical velocity at the time which we hit the ground, which was 5 seconds. So its value then will be -30 metres per second. And because these are vectors then, we're going to recombine these to find the magnitude of the resultant vector and the orientation of the resultant vector. So the magnitude, first of all, is simply given by the fact that we can combine these two sides here to get this diagonal. Or in other words, use Pythagoras. So the length of that resultant vector there, which is either the magnitude of the horizontal velocity or the impact speed, if we put it like that, is the square root of these two, which comes out to be, I think, 10 root 21 when we simplify that. And what is the orientation of that vector? Well, we can just apply ordinary trig, so tan of theta, if I put theta as the angle to the horizontal there, is the opposite over the adjacent. So theta is the angle whose tan is that, which comes out to be 41 degrees. So theta is 41 degrees to the horizontal. I could have said that it's going to be 49 degrees to the vertical as well. So unless it specifies it in the question, that's entirely up to you. Now, our next question is a tough one. This would be quite a difficult question, and it's going to be a long question. So a gun at O fires shells with an initial speed of 200, but a variable angle of inclination. So when we look at our initial sketch here, this is all that we've got. Fires it at 200 metres per second. We don't know the angle. Looks like I've substituted a theta for an alpha, but it makes no difference, of course. So first thing is just to get our equations. So horizontally, we've got these conditions which always apply. We run through and we get our two equations as we did before by successively integrating and finding the constants of integration. So we get that the initial velocity horizontally is 200 cos theta, and that's the best we can do. We only get an expression for it. And the initial displacement is that 200 cos theta times t plus c, and c works out to be 0. Vertically, we integrate and we get this, and initially the velocity is 200 sine theta, so that gives us this equation for our velocity in the vertical direction, and when we integrate that again, we get this as our equation for displacement in the vertical direction. So we've got the tools that we need to then try and solve this problem. So the first part is find two possible angles at which the gun can be set so that it will hit a fortress 2 kilometres away on top of a mountain 1,000 metres high. So we want to know what the values of theta are so that when x equals 2,000, y equals 1,000. So that's going to require us to solve some simultaneous equations because we don't have all the information. So knowing that x, the horizontal displacement, is that, which gives us that 20 equals cos theta on t, and knowing that vertically the displacement is this, which we equate to our velocity, then what we can do at that stage is to say that from our first equation up here, this one, t is 10 on cos theta, because, whoops, just hit a wrong key. So t equals 10 on cos theta from this step up here. And if we take that value of t equals 10 on cos theta and put that into our equation 2, so that we're eliminating the parameter t, we get this equation, which looks awful, but we just persevere with it because we have all the mathematical skills to cope with this. So this is going to be 500 on cos squared, so if we bring that over to the left hand side, 500 on cos squared will be 500 sec squared. This term, if we take that over to the left hand side, that'll be 2000 sine on cos, which is just tan, and the 1000 is sitting there. And what we can see is that at least we can make life nicer by dividing through by 500. So we get to this equation, and then we remember that sec squared is 1 plus tan squared. So replacing that, the sec squared becomes tan squared plus 1, which is added on to 3. So now, finally, we see that we have a nice quadratic in tan. Pushing on with that, when we factorise that, we get tan theta minus 3, tan theta minus 1 equals 0. And our two angles are from this first bracket, tan theta equals 1, meaning theta is 45. It's an exact value. Tan theta equals 3, we have to go to the calculator to get tan to the minus 1 of 3, and it's 71 degrees 34. So they're the two possible angles at which the gun can be set so that it hits the mountain, which is located, it hits the fortress, which is located there. Now the next part is just an odd question. Show the two angles that are equally inclined to OF and to the vertical. So if we think about the diagram for the fortress, 2000 across and 1000 up, then one launch angle of 45 degrees is at 18 degrees 26 to that. The other launch angle at 71.34 is at 18 degrees 26 to the vertical. So that's an odd question. It has nothing to do with projectile motion. Then in part C, find the corresponding flight times and the impact speeds and angles. Now I'm only going to do one of these because it's just a repeat of the process. So when we look at 45 degrees, so obviously I've picked the easiest one, when alpha, theta, when it's 45 degrees, then the time of flight becomes 10 on cos 45, which is 10 root 2 seconds, and the horizontal velocity is going to be, when we plug 10 root 2 into our equation here, it's going to work out to be 0. So did I just say horizontal? I meant vertical. So the vertical velocity is 0. So the only component of velocity which is acting for this particular flight path is the horizontal component, which is 100 root 2 meters per second. So when we fire at 45, what must be happening is that the fortress is over here, sitting on top of the tower. We're firing at 45 degrees launch angle, and we're coming up, it must be hitting just at the top of the parabola that it would have followed. When we fire more vertically, it's going to be hitting the fortress on the way down. So that for the second part of this question, we're going to have to get our horizontal velocity, which was our 100 root 2. We're going to have to calculate the vertical component of velocity at the time that we hit, which will be different because it's a longer path there. And we're going to have to add those two vectors to get the resultant vector, as we did in the first example. So have a look at this solution is in the textbook. Have a look at that if you'd wish. Otherwise, as long as you know how you would do it, that's probably most important. And then try to put together the big ideas in this topic. What exactly is it that characterises projectile motion? How do we set the problems up to start with? What are the things that identify such things as the time of flight, the position of maximum height, the horizontal range, and so on? And have a go at these questions.